Thank you everyone for joining us for our July community meeting. We have a really awesome lineup today of presentations from the community. Maxim is going to kick it off for us with a presentation on his recently merged work on hasher-based hashing. And then we're going to hear from the 3 winners of our recent Modular Hack Weekend. So we'll hear from Martin, who implemented the Fast Fourier Transform. We'll hear from Seth, who built an overlap detection library for bioinformatics. And then finally, we will hear from Thomas, who created a quantum circuit simulator. And then, as usual, we will wrap it up with Q&A at the end. So I'm going to hand it off to Maxim to get us started.
All right, thank you very much. Let me just share my screen. Just to say, there it is. And let's share the text set. You should be able to see my screen right now, right? With the presentation. To have like a small kickoff, who's familiar with the TV show that I picked today? It's called What We Do in the Shadows. It's not that popular, but it's actually quite. I like the humor, and the character I picked. He's an energy vampire, basically, right? So like, just to get a little bit of the background and the maybe jokes. Right. So hasher-based hashing. Right. So the first question is why, and this is also why I picked this person, because it's a breaking change, right? So like it feels like, okay, I could say I like feed on misery of people. This is why I wanted to push a breaking change and just let people change all their code to kind of to like suffer through refactoring. But generally, why we would like to have hasher-based hashing and why I proposed it, there are mainly 3 points. This is security and developer experience. Normally, these 2 things are actually opposites, right? You normally say like, okay, if you have security, then the developer experience gets worse, or if you have nice developer experience, then security suffers. In this case, it's actually a win-win, and we will talk about why in a second. Then we have more flexibility with this change, and also it allows us to get better performance generally for the dictionary, for generation of hashes, and so on and so forth. Well, so how it worked before, it was just basically the hashable trait was typical what we also know from Python. We just basically, we need to implement this method, hash, which just tells you, okay, I need an int, right? And if you have a struct, let's say person, and you want to make it hashable, and you have just first name, last name, and age, you could just panic and say like, okay, I'll just return 42 because I don't know what kind of int can I actually return. So like, but this would be a very bad idea because then everything will collide. You could also say like, okay, I actually have age, it's also a number, so I will just cast it to an int. This would be also a bad idea, actually. Then you could say, oh, we have a hash function in standard library, and we have a first name. So let's have first name, but it's also will lead to lots of collision. It's not a really great idea. What you generally want to do is to say like, okay, maybe if you have a field which is an ID by itself, then you can just hash this ID and you good. But if you have a struct which doesn't have like actual ID and the identity is a combination of multiple fields, then you need to combine them. And then just the question is, okay, how would I do it at all? Like here is an example. I could say I create a transient string, which then I will hash, right? And here is the problem with performance, because you actually having a transient object where you allocate on the heap something just to calculate a hash and then return an int. And this is, you can do it. You basically do it in Python this ways. Normally there you do tuples, but again, they are still objects, right? So like it's actually not that performant. And it's something which developer need to think about, because they could also go with some other solutions. They actually need to understand, okay, how do I combine multiple fields, multiple values into one integer number, you know? How it works now is basically following. Now you if you have a hashable, you also need to implement the method which gets a mutable hasher, and then you can just update the hasher with the data that you would like to contribute to the hash value. So you just say hasher update first name, hasher update last name, hasher update self, age, and you're done. Right, so like this actually simplifies your mental load as a developer. You just, if you would, for example, let's say you have a struct with an ID and this ID is unique, then you could just say like, okay, hasher update with self ID, and this would be also enough. So there, it's actually much simpler, and the developer experience is actually quite nicer when you know how it works. So basically what we did is we switched from call return paradigm to data flow. Call return paradigm means that you always need to return something. Here, as you can see from before, we actually, this method doesn't return anything anymore. You just need to feed the hasher, and then everything works by magic, right? Which is not. Well, the question is, well, when we implement a hashable struct, do we just need to decide what values to contribute? Sadly, not always. Sometimes you still need to think about stuff, but it's also would be in the other situation. We have in our standard library, we also have a struct set, which the keys are hashable, but it is itself also hashable. And here, the problem with this data structure is that it's order independent. So what we do in the standard library, actually, we say like, okay, we would like to iterate over each value. We create a hash value out of it, and then we just feed the hasher with hash value. Here, we just XOR them. It's not super secure. It's actually not that nice. The problem is we can't tell if the hasher can combine the values actually commutatively. If it can't, and normally they can't do this, then if you say you have a set of 1, 2, 3, and then you have a set of 3 to 1, they actually should produce the same hash, but it could happen that you will get a different hash if you would just call hasher update with each value of thing itself. What we could also do, if we would have a sorted set, then we could just say like, okay, we just run through the sorted elements, and then it would be perfect. Then it would work just with update. We don't have to do we won't have any mental load in a way. So keep it in mind when you actually implementing hash methods, that it's sometimes like this commutative situation might be considered. Okay, what kind of hash function do we have currently? We have FNV1A, which is a very simple hash function, actually. Then we have a hasher. This is a port from Rust. It's a very fast hash function, but sadly, at this point in time, it doesn't work at compile time. And we have like what we had previously in standard library is DGBX33A. I kept it just for compatibility reasons, in case that if someone stored some values which we created in previous standard library, then they could just use this hasher again to get basically the same values back. But otherwise, I would highly recommend if you need something at runtime, then use a hasher. This is actually also the default hasher currently. And if you need to do something at compile time, then please use FNV1A. It also has an alias of default compile time hasher, which after this bug is fixed for in the compiler, then we would be able to just use a hasher for everything, because it's generally faster and it's gives also much better quality of hash values. Right. Can I implement my own hash functions? Yes, you can. I also talked about in the modular community meeting number 7. I had a presentation called hash functions and where to find them. If you are interested, you can look it up again. There I also talked a little bit deeper about what are hash functions, how they are implemented, what is a good hash function, and so on and so forth. Generally, if you want to implement your own hasher function, then you need to implement the hasher trait. It's actually quite simple. You need to provide an init method. You need to provide an update with bytes. So basically, this is a method where you put just basically just bytes with a length, right? So like an unsafe pointer to unit 8 with a length. Then we also have like update with SIMD. This is mainly for some performance optimization that you can use, because SIMD has a known length. Hence, you can do hashing much faster this way than here, where the length is only known at runtime. And this update is basically just a default one. I will just show you how it's implemented in a second. So as an example, this is everything we do for FNV1A. This is also a very simple algorithm, actually. So what it does in the beginning, when we initialize, we have this magic number, which kind of like randomizes your input in a way. This is quite a random bit pattern. Then when you get the bytes, you basically just for loop over them, XOR them with the previous one, and then multiply by this other magic number. This is basically the specification of FNV1A hash as is. For the update with SIMD, we do the same thing, but as you can see, we have here at parameter for loops, which means that they will be just unrolled. So we won't have a real for loop here. We just unroll the algorithm, hence it will be a little bit faster to run for SIMDs. With update, you always just write value and hash with itself, with self. So with this hasher, so you just say like, okay, I would like to be injected into this value, which is hashable. And we finish in FNV1A is just returning the value here. With other algorithms, they do more complex routines when you finish stuff. But again, you can basically see which function you would like to implement, and everything is fine. To use a custom hasher, we can do following. If you would just try to compute a hash, you just provide hasher type as a compile time parameter, or if you have a dict, you can also say like this is key, this is value, and this is the special hasher which you would like to give it, right? So like then everything works. You can just think about that for your use case, you would like to have like a different hasher because you know on your data it will run faster, better, whatever, right? So like it's up to you. Right. What is the reward for a job well done? More work normally, right? So more work. What is the future work? As I mentioned already, there is a bug in the compiler, which is already, as far as I know, it's already been worked on from the compiler team. So this is already in progress. Then we have also a feature request where we would like to benchmark the dict and see if there are better data structures, which will make our dict much faster. So like, for example, Swiss table by Google is one example, and there are a few others. I'm looking into this one to kind of try out and see what can be done. Then it would be really great. And as far as I know, it's somewhere on the roadmap if the compiler could actually auto-generate hash methods for us, right? So like if it's declared hashable and all the properties are hashable, then it would just generate it the same way it does for copyable or movable, right? And if you would like to change it, then you just declare it yourself. If, for example, you have multiple fields and you have just one ID and you would like to just contribute the ID and not everything else, just overwrite the hash method and just provide a small thing. Otherwise, it would be nice if it would auto-generate. Then one thing which we currently don't do is randomized hash seed at runtime, mainly because we don't have good support for global variables here. Because like in here, it would be like specifically if you're building web servers, web applications, they like when the server starts, then it just generates a random seed, and this seed is used so that it's much harder to kind of have like an denial of service attack based on hash maps.
Maxim, for that, you might want to look inside the Python object stuff.
Okay.
Python object has a special fast path for accessing global variables. We could extend that to privilege hashing. The one thing to think about is like we don't want to pull in a whole bunch of dependencies into like GPU programs and stuff like this, and so it should be. We need to figure out how to conditionalize it, but the global variable thing for global variables in Mojo are generally cursed, but the using that API is fine. And here you just want like an int, and so it's fine.
Yeah. So like again, it's a question a little bit like the current hashers are deterministic, so like they won't have randomization. But again, you could actually write your own hasher and then just make it kind of like randomize at runtime while you kind of generating something in the beginning, storing it globally.
Let's not deep dive on it here because I think it's probably sure. We can break it out and have a longer discussion. But I mean, I'm agreeing with you. Like you generally want things to by default be secure, and so let's just figure that out offline.
All right, cool. Right, and last one, which I already wrote in my proposal, like back in the day, like it might be nice to have a parametric traits where we could say like this hasher, I would like to have a hasher which generates, not now currently we say by default they generate uint64. It could be maybe interesting to be able to parameterize it, to say like I would like to have a hasher which generate U32, or maybe I would like to have a cryptographic hasher which generate U256 and so on and so forth. Because like, for example, FNV18, the implementation you saw previously, it's the U64 implementation. There is a special implementation for U32, mainly is just about different magic numbers, right? So like in this simple algorithm, but in more complex algorithms, you could actually think about maybe to do it a little bit like more different and more differentiated. Okay, then thank you very much. I'm done. Do we have any questions?
Awesome. Thank you so much, Maxim. Looks like we have a question in the comments. Are we looking at figuring out consistent hashing between different architectures / compute devices? Would maybe need to handle different integer encodings, endianness, sign bit versus 2's comp may all show up on the same system, max with GPU. That's from Sawyer.
I think now specifically when we talk about FNV1A, this will should be actually work on everything equally, I would say. With a hasher, I'm not 100% sure, but then again, it's all about generally the implementation of the hasher trait. If you will implement something which is already like platform aware or platform agnostic, then it should be fine. In my current opinion, I would have to like approve it, but and look a little bit deeper into it. But I would say currently it even the hashes that we have should be actually fine, and otherwise it should be possible to just implement a specific hasher which would give it both. And we could also, if you do, then you can also contribute it to the standard library, and then yeah, I think how things are currently, we can extend these things quite easily, as far as I can tell at this point in time. Any more questions?
This is great, Maxim. Thanks for giving this presentation. One of the things that you highlighted that I just want to keep emphasizing is you've effectively generalized things a lot more. Before, the hash, both the function and the hasher that was used in dict and set was effectively hard-coded in the library and couldn't be controlled by users. And we've lifted that up at several dimensions, both at the hash function and then the allowing to inject different hashers to dict and set and propagate this through our type system. So this is great on many levels.
Thank you. All right.
Awesome.
Then thank you very much.
Other questions?
I stop sharing.
Thank you so much. That was great. Now I'm going to hand it over to Martin.
Let me share my screen. I'm just going to share the whole screen. Okay, can you guys see this?
Yeah, we can
Yep.
do it.
Okay. So basically, I'm not gonna give the whole context on what Fourier transform does, but basically it's taking from a signal from one plane up to the Fourier plane, which is basically a slice through a Laplace space. But it's basically a way to like decompose signals into their frequency domain elements. So what you normally do is you multiply a signal by certain what they're called twiddle factors, which is basically a way to say like you literally turn them into spinners by multiplying them with complex values in stages. And the algorithm that I developed was based on this butterfly diagram, which is what normally gets used in like signal processing classes in university, which is basically a radix 2 algorithm. I've been reading up on that, and this was the actual core of the algorithm that I submitted to the hackathon. And I've since developed it a bit more. But the basic concept is you get the twiddle factors array in cache. And so you index into that and multiply the x1 factor, which is always like the lower element, the one that whose arrow points up, that gets multiplied by the twiddle factor, and the x0 line would be the top line in the butterfly diagram that always points down. That gets only added, and the other gets multiplied, and so you can just do a fuse, multiply, and add. And this was the core of the algorithm. But I've since like tried to generalize it a bit and also do a bunch of tricks to get a bit more performance out. So this is the previous path, which is a simple one. But you also get, when you know that the imaginary part of the like twiddle factor is, for example, -1, then it's just since the magnitude is always going to be 1 since we're working in the unit circle, you just know that it's just a sign flip of the sign flip and change of like places. So the imaginary part goes in the real part, and you just do a sign change for the real part into the imaginary part. And then it's, since the radix 2, it's like a symmetric algorithm, you can also update the lower element as well, not just the upper lines, just also the lower one. I'm gonna explain a bit later why there's a difference there. But basically, I've also been reading up on like what the implementations do and like FPGAs. There's also some ASICs, but they develop them in their papers, talk about how they developed it in FPGAs, and then they just synthesize it with whatever tool, I don't remember, Verilog or whatever. So I've been reading up on what other algorithms are, like radix 3, radix 4, radix 5, radix 7. And basically what CUDA does is they've got implementations for radix 2, 3, 5, and 7. At least that's what they publicly say. They probably have a radix 4 as well. And why? The thing is, this algorithm, for example, radix 2, provides an improvement of log 2 to the actual computation amount versus if you would have done the classic dot product and whole matrix multiplication that you have to do for Fourier transform. Radix 3 gives a log 3 improvement, but only for values which are divisible by 3. So what you do, these are called like mixed radix algorithms. So you decompose a signal length into, let's say, 15. So you know 15 is 3 times 5. So you run it once through the radix 3 algorithm and once through the radix 5. That way you got the improvement on both sides. So I just started like looking into how it would implement the code. I think this code should work. Like it's pretty basic and simple in a way. It's just literally implementing the multiplications and total factors for these values exactly. But because I, like Maxim said, I like suffering, I also started looking into maybe generalizing this into a radix n and making use of Mojo's incredible parameter systems. So if you know the base at compile time, and if I actually manage to make this work, this would be crazy because this gives log n performance improvement, like multiplication wise. But there should be a limit because you're not going to be doing like a radix 1024, for example. You're gonna like oversaturate the ALUs. So that's why I had this question like the in Discord for the Max on the Max GPU channel, because I don't know like how far to push this. Like for example, if you got I don't know 1024, maybe it's more worth it to like split it in half and do radix like 512, or maybe the square root like radix. I think it was 64 the number. So I'm just exploring a bunch of avenues. There's also a bunch of optimizations that you can do. For example, like at compile them, since you know that you're in stage 0, you're gonna know like the total factor is only gonna be like either 1, 0 or -1, 0, for example. For base 2, there's also other specific optimizations for the other bases. So this has the potential to literally be a mixed radix algorithm implemented in just one function. And there's also a bunch of tricks that you can do if you know that the input is a real signal. You can also do a bunch of shortcuts. So this at the same time could be a generic radix n algorithm and also a RFFT implementation, which has a bunch of tricks. Like I implemented most of them for the radix 2 algorithm, but I'm trying to port them more over to the generic implementation. You can basically do in some places like half of the operations, for example, since you know that the right side is going to be like 0 because it's at the stage 0. And so at the last stage, you can also do a bunch of tricks, which is basically, since you know this is a real signal input, the half of the output signal is actually a symmetric conjugate of the first half, except the 0th element. But there's a bunch of tricks that you can do. So you do literally half the operations in the last stage. So I'm just like going over all of these tricks, all of these elements, and trying to come up with like something that's actually generic. So that's also a bit of a question that I have for like the modular team. Like, how soon do you want to have this like incorporated? Because I've got a lot of work here if I really want to make this work generically.
I'm happy to answer that. So like with most things, both in the standard library and the kernel library, like it's hill climb thing. So like don't feel the need to overly generalize as long as you're defensive and add constraints with the cases that you do support. Like for example, I wouldn't wait to, push on radix n if you have like known just a radix 2, 3 or 3 and 5, for example, like that. I would focus on correctness and testing, and then we just explain what is and is not supported and go from there. We would be happy to accept a contribution in the kernel library for FFT and RFFT, regardless of which radix are used.
Okay, but the thing is, if I do that, then it will be like it will need some heavy refactoring, like a couple of weeks later. Like I'm still like hard developing this.
So in your mind, what is?
I'm just asking, like, what are you months, years? I don't know how much time this will take me, but I'm like exploring this on my days off, etc. So
yeah, I mean, what would it take to clean it up, and what would be the limitations if we were to accept this in the short time frame, say in July? Like Is that possible? Do you need a lot of work? Are we looking at August? I'm
No,
happy to talk offline and
I've
we can look at the trade-offs.
Yeah, I mean, I've mostly set the stage up for this to like be merged, but I'm still like changing my mind about some stuff and just changing the whole architecture of some things. But most of it should work fine. But I'm still like, I have to set up the whole testing suite, like very thorough and very different like sizes and examples. And also I've got to set some benchmarking because it doesn't make sense to merge this, replace it QFFT and it'd be like half the performance and whatnot.
Exactly. The minimum requirements here, from my perspective, would be correctness and performance. So I would recommend you take a look at KBench, which is fully open source now, and you can look at it because the high level business question you want to answer is when would it make sense to use this over falling back to CUFFT? If the answer is never, then it may not make, or like this doesn't provide differentiated value add, then it doesn't make sense to use it yet. When do we get that inflection point where it makes sense to use instead of CUFFT? And can we ensure it's still correct for those cases that are supported? Those are the things that I would focus on from my perspective.
Yeah, that makes sense.
Happy to talk more offline. We can talk about, correctness and benchmarking tools and that sort of thing.
Yeah, I just like I'm at this stage where I'm like exploring still, so I didn't want to put too much time into like benchmarking something that I'm gonna just throw out the window and start maybe again because I might just start with another approach this next week.
Yeah, one
So I
thing
guess
that
we'll
may
see.
guide whether you throw things out or not is by benchmarking. It'd be good to understand where you're at and where you want to go and what that gap is and how you're going to close that.
Yeah, okay. Okay, we'll talk more offline then. I don't know if
Sounds
anyone's
good.
got any questions.
Yeah, any other questions for Martin? And thank you, Martin.
I think I went a bit too fast, but yeah, it's basically an overview what I've been working on.
Yeah, this is great.
Super exciting.
I mean, it's pretty cool, like developing this generically. It's crazy. I don't even want to see the C++ code equivalent.
Yeah,
So
exactly.
stuff
I mean,
sharing.
it would, I mean, just a totally random thing, it would be interesting to just do like line of code difference between the generic implementation and then all the concrete implementations it replaces. That'd be crazy.
Yeah, I mean, I'm pretty excited like for the generic implementation.
Someone in the chat is asking for a link to your code if you're able to share also. I don't know if it's
It's the same link as the hackathon. It's still developing in the same repo.
I'll put
Let
it
me
in
just
there.
I'll send it to.
Awesome. Thank you again, Martin.
Yeah, thanks, y'all.
Now we're going to hear from Seth.
Sorry, Zoom hid my mute button there for a second.
No worries.
Yeah, so my project was Mojo-Lapper. Feel free to check out the GitHub repo or the thread on the forum, which was a longer link, so I didn't stick it on here. Mojo-Lapper, at its core, is an implementation of the binary interval search algorithm that was outlined in this 2013 paper. It's a fairly straightforward way of counting the number of intervals that your query overlaps. So if I have a set of 1,000 intervals and I have one query that is, start 1 and 100, I want to get the total number of intervals in my reference set that my query overlaps, which is a bit distinct from other interval things that you might want to do, like enumerate all the intervals that you overlap, which do have faster solutions out there. So how this works is you take all the start positions of your database of intervals and sort them by start. You take all your end positions and sort them. Then you do a binary search of the query end position against your starts and a binary search of your query start position versus the ends. And you can take the difference between the two indexes found. And that difference is the total number of overlaps for your query. So it's nice because it gives you two binary searches to get an answer where you might otherwise have to do a lot of iteration after finding the first lower bound. I thought it'd be fun to put this on a GPU because the original implementation of this did include a CUDA kernel, but it's from think I said 2013 is when that originally came out. And the original paper didn't include a one-to-one benchmark versus the CPU implementation. It just had kind of a macro benchmark of a big simulation that they were doing. And since they didn't include the one-to-one benchmark, I kind of assumed that it wasn't going to be that fast. And that the GPU version might be a little bit faster than the CPU version, but because of the memory access pattern of a binary search where you're jumping all over the place and threads are not going to necessarily be jumping to similar locations, that would not end up going well on a GPU. The short answer is that I was wrong. It actually works just fine. If you throw enough threads at anything, it will still work pretty well. So this table is showing the comparison between the CPU and GPU versions of the counting, and then also the counting with a naive approach where you just do a single binary search to find the first possible overlap for your query. And then you iterate through the rest of your intervals after that first match to find any further overlaps and count them. So you can see that just on the CPU, the bits algorithm is about 10 times faster than the naive approach. And then on the GPU, we get about the same ratio of a little bit better than 10 times faster, which again kind of makes sense because less iteration is good. And then the total speed up. So doing the bits algorithm, this is the GPU version versus the CPU version is 140x faster for the bits algorithm. This isn't doing anything fancy, really. It's just relying on some dynamic scheduling. So I'm just telling it, run one instance of this per thread, which I based off of a paper that came out a couple months ago called Binary Search is All You Need. That's about a faster version of doing binary search on GPUs that I'll talk about a little bit more in a second. And they found that leaving it up to the GPU scheduler tended to be better than trying to do anything fancy yourself. So I didn't try any other ways, at least not yet. And then on the right is the Mojo code for the kernel. So we saw the method a second ago down here, this count. Like this is the actual method at the core. Lower bound is just the binary search up to the first element that is less than or equal to your query. And the kernel is running that lapper.count method internally. So one of the cool things about this library is it gave me a chance to play around with taking a data structure and making it work on the CPU and the GPU by swapping around how the memory is used under the hood a little bit. But you get to use the same API both in your kernel as you would on the CPU itself, which results in this pretty simplistic looking kernel where all you really need to do is sort out your normal thread math and then throw it into the function, which was pretty neat. Some takeaways from this, just try running your algorithm on the GPU. Like I said a little bit ago, sometimes if you just throw enough threads at something, it makes all your problems go away and it just works. The barrier to entry has never been lower as far as I'm concerned, at least. And the design space around GPU, CPU data structures is going to be a lot of fun to work with the caveat for both of these last two statements of I've never written any CUDA. So maybe things are just fine, but it doesn't look like they're fine when I go and look at CUDA kernels. There is some further work that could be done on this that I would love to do at a future point, such as moving all of the Lapper construction stuff onto the GPU and doing their array sorting with a radix sort as well. I'm currently just using the standard library sort. I do have a CPU version of radix sort, which I think I actually stole directly from one of Maxim's repos earlier. I'd also like to try swapping out the underlying data structure to a static B tree, also sometimes known as an S tree, I believe, to see if that can improve the memory access patterns and speed up the GPU version even further. That's everything. Any questions?
That was great. Thank you so much, Seth.
Yeah, I totally agree with your assessment of the situation. So much opportunity here. That's super cool.
Any questions for Seth? All right, well, it was just so comprehensive that nobody has any questions.
I have a small question. I wanted to ask that this data layout is basically an ideal CPU cache-friendly data layout, and how do you think uh, it basically performed so well on a GPU kernel and a naive GPU kernel?
Why did it perform well on the GPU? That's a good question. I think one detail that I didn't include is that or maybe it was on the slide and I didn't read it. I did sort the queries prior to running them, which should give it a little bit better of a chance of having two threads that are, next to each other, accessing similar places in memory. But I think the only other answer that I can come up with is that GPUs have gotten a little bit better at handling this sort of memory access pattern, even though it's all over the place, which still runs counterintuitive to what is in the textbook necessarily, which led to my just try it ask. But I do think that if there's going to be improvements in performance here, it's going to be just fixing the memory locality and switching to even use like the static B tree, S tree are more cache friendly for a CPU. So use all those learnings from cache friendly CPU algorithms and put them on a GPU as well.
Awesome. Any other questions for Seth?
I had one non-urgent question. I dropped it in the chat, but Seth, I'm curious to know if you played with the interval tree data type that's in the standard library at all. Should be roughly equivalent, but I was curious to know if you got any experience in the wild with it.
I did try it with a little bit of a benchmark situation that I set up, but it wasn't a very nice comparison because I think for reasons that I never looked further into, I couldn't actually get the interval tree from the standard library to like finish creating. Like I was putting too many elements into it. I'm not sure what the issue was with it, and I haven't gone back to try and sort out why, because I did want to see like how the comparison would land. Theoretically, my data structure has some glaring holes in it, where if you have like one interval that spans your whole interval set, you have to iterate all the intervals in your set if you're trying to like find something. It's still very fast for the count situation, but it's suboptimal and therefore wouldn't be like a good candidate for a general purpose situation. Only if you know your data type fits this nicely, does this happen to be a useful setup.
Right, makes sense. I just wanted to call it out in case you hadn't seen it. A, because ours is basic as well, and so we'd welcome any bug fixes, improvements, that sort of thing. So let me know if you dive into it.
Yeah, we'll do.
I'd be curious to know what you find. Thanks.
Thank you. And thank you again, Seth. All right, so our last presentation is going to come from Thomas.
Okay, can you hear me?
Yes.
Thank you. Okay. I don't know. Can you see the thing on the right? Yeah.
Yeah, we can see your screen.
No, but I mean, oh, sorry. Yeah, can you see the zoom too on my screen on the?
We can just see your slides.
Perfect. Okay, so yeah, I wanted to first, yeah, so what I'm going to present is QLabs. It's a quantum circuit simulator that uses GPU acceleration that I added during the hackathon. And so maybe I will talk a bit about what I do. So I'm just going to graduate from my computer science master, and I'm going to move to a PhD in quantum computing. So why did I decided to create this simulator? Because it is a simulator. So firstly, to myself better understand the limitation and also what we can do when we simulate a quantum circuit, but if we do this classically on a classical computer, as we see after this, the limitations. Also but of course, to allow other people to have those same sort of insights, and also to learn about how the quantum simulation can be done. And lastly, I wanted to have a library that I could use in the future where I could analyze the different aspects of quantum states and their evolution, because this is difficult with the existing libraries. And if I have my own, I can add more functionalities that will help me do this, and also maybe others. So yes. Oops. So I did not created that from just my head. I took inspiration from a recent paper, how to write a simulator for quantum circuit from scratch. They propose an implementation in just 2009 of a state vector simulator. We see what is a state vector, and the implementation is in JavaScript. So I did it in Mojo. That is, we can compile, we can use GPU. So this is why I did it on Mojo. And they say that it could be done on GPU in their conclusion. So this is why was what I decided to do. So just also to give you a bit of context about what is the objective. So the objective is to simulate the kind of circuit that we have on the left here, the gate circuit. And this is a quantum circuit, so it means that we have qubits instead of bits. So here we have 3 qubits, and we apply some operations, and it will change the state of those qubits. And when we talk of a state, we know that a qubit is what is different from a bit is that it can be in a superposition. This is what we have here on the right. We have the state vector representation of a qubit, single qubit here Q0, and it's a superposition of the basis 0 and the basis vector 1. And so this creates a vector of size 2. If we extend this to 2 qubits, we can have more superpositions. And so the basis vectors become of size 4. And so we see that there is an exponential growth in the size of the state vector. So this is why when we simulate it classically, we are limited by the memory of classical computers. Okay, and also what the library is able to do as of now, it has 2 types of control, a low-level control that was inspired by the paper, and a high-level control that was inspired from the usual quantum simulator libraries that exist, like Qiskit and PennyLane. And also it supports for user-defined operations. As we see, we apply some operation that change the qubits. And I added the Ridakaton GPU acceleration for some of the low-level functions or low-level primitives. And also adding it to the high-level control with just one argument that we change from true to false if we want to use the GPU or the CPU. I included some tests, some non-regression tests, of course, and some benchmark to compare the CPU and GPU implementation. And so what is the low-level control that we need and that was inspired from the paper? There are 3 main functions. A qubit-wise multiply. This will transform a state, and this will apply a given quantum operation. It can be a single qubit gate or a double qubit gate, or triple qubit gate if you wanted, and more. And this function has been optimized for quantum simulation. So it doesn't use matrix multiplication. It uses a smart things that we will see after. And there are 2 more functions, apply swap, that is a type of gate, and partial trace that allows for to compute some statistics of in the circuit. And those 2 have been also highly optimized for quantum simulation, and those I have not implemented for GPU yet. When we simulate, we can use some abstraction. For example, for the state vector, it can be composed of a list of complex float. And for a gate, it's a list of complex float. When we move on to the high level, it uses those 3 functions, but it gives us an overview, a high level control that we will see after. And for this, I defined 2 classes, a gate circuit, where we can create a circuit by adding gates, and then a state vector simulator, where we can feed a circuit and an initial state to run the simulation. And this one has some partially GPU support. Also, I wanted to say it was my first time. It was my first time working on the Mojo project and also on a GPU programming project. I never done CUDA programming before too, and also my first time using a Pixie more in depth. And so I created those tasks, but more importantly, in Pixie, we can use caching, and that's really good for a project where we have to iterate our debugging. So we don't have to, for example, here, we can define input and outputs, and if it detects that there was no changes, it will move on this task and not perform it. And also, since I'm a bit lazy, I don't like to write Pixie run and the command. I made a make file that can just pass my make command to a Pixie run command line. Okay, so here we see I don't know if I'm taking too much time. Here we see the use of low-level control for CPU. We are trying to simulate this circuit, a 3-qubit circuit with some gates. So for this, we define 2 states, and we use a function called qubitwise multiply, this time in place. So we give it a matrix. Here, for example, the Hadamard gate, this gate, we say we want to apply to the qubit 1, and we give the input state and the output state. And for the next gate, we inverse those two so that we don't have to allocate new memory every time. But I noticed that on CPU, if we don't do this trick and if we have a function that outputs a value, Mojo will efficiently optimize it, and there is a very minimal difference. But having this help us to map this then to GPU, because this is the approach that we want for GPU. We don't want to reallocate every time. So this is just partially because we have to apply this for all of the gates. If we want to have the abstract control, the higher level control, in the same way we can you can apply gates, but this is on a gate circuit. We see that it's easier to write. We just apply a gate to a given qubit. And then we can run the simulation using the state vector simulator and the initial state. And this is easier to work with. But it doesn't give us the insight that the low-level control gives us. And lastly, if we want to do this on GPU, we also have to define the gate circuit and the initial state, but we also have to define some compile time parameters. At the time of the hackathon, we have to define more parameters that I want to, because the circuit, they are defined at runtime. So we have to define some things at compile time, but if we were to define the circuit at compile time, we could infer this from the circuit, and we don't have to put those parameters here. This is one of the objectives after. But as we see, it's just one parameter used, or one argument use GPU if available, set to true, that will make us use the GPU. If we go into details into the function itself that does the computation, it is composed of 3 steps. A first step, so it takes the quantum state, the constant state output. The first step is just to set up the algorithm as it is defined in the paper. The second state is to prepare the output. So here we copy the input to the output, and then apply some transformation to the output to simulate or to apply the transformation of the gate circuit of the gate quantum gate. So I will not go into the details of the computation because this is a optimization that was found or that is used and is explained in their paper, tutorial paper. If we want to do this on GPU, we have to change the signature of the function. We have to add some parameters, but also we have to use this time layout tensors instead of structure. And we have to to change the arguments to use layout tensors for the input quantum state and the real and the imaginary part that is composed of floats. Step 1 stays the same, but for step 2 we can copy each thread can copy one element from the input to the output, so it's more efficient. That's not just one thread doing all of the work. And for the gate and for the actual computation, we see also here step 3. For the actual computation, it's also one trade that will, it's also all of the trade that will participate. It will take part in the computation, so it is more efficient. If we compare the CPU and GPU, here we have some benchmark results. What we want to compare is with different number of qubits. So on the right here, with the different size of state vector, we see that CPU is pretty, so it has an exponential growth, as we see the y-axis is logarithmic. The GPU is slower at first, but for a bigger number of qubits, it is 100 times faster than the CPU, sorry. And so if we look in this range of, for example, 13 qubits, when we increase the number of gates, the number of operations that we do, we see that also it scales better on GPU because we are at this point where GPU is better to use than the CPU in that case. So yes, what I want to add in the future for this project, of course, to add GPU support for all of the low-level primitives, so apply swap and the others. Improving the current GPU kernel, because as we see, it is a memory bound, so maybe there is some tricks to do where we can recompute everything and only store partially the state vector. Also implement naive versions of the low-level primitives, because for learning and teaching purposes, to show that it doesn't have to be as complicated as they are at the moment. And extend on the capabilities, for example, tracking some statistic during the execution of the circuit, having gradient computation, but since Mojo doesn't have autodiff, it's pretty difficult. Maybe implementing tensor networks, they can be used for quantum circuit simulation, and having more degrees of abstractions too. So yeah, thank you. If you have questions, don't hesitate.
Thank you so much, Thomas. Any questions for Thomas?
I guess I'll go ahead. So this, like, simulating quantum circuits was basically my bachelor's thesis. I'm doing quantum information science now for my master's, so this is very interesting. If you want, I have some papers I think you would be interested in.
Yeah.
Any way to reach you?
I don't see your name. Is it Asmus? Oh
Yeah.
On Discord. I will send the message in the chat after.
All right. I'll send my name in the chat. Thank you.
Thank you. So did you have a question, or just thank you for sharing?
No, it was a very good presentation. I'm happy.
Okay. Thank you.
Very cool. Any other questions for Thomas? Going once, going twice. All right. Well, thank you again, Thomas. That was really, really great.
Thank you.
Now we're going to move into some Q&A. Let me share my screen. We do have one question that was submitted ahead of time. Can everybody see my screen? I think so. So this question is, when is Mojo support going to come in for other distributions of Linux? And also, when will the Mojo LSP support come for other editors like Vim? I think Brad is going to answer this one.
Yeah, it's so the Linux support question. There are two different areas here. I think one of the original phrasing this question involved like Nix OS and where can we come there. But then also, like, there's the general question of like expanding to other Linux distributions. So one of the items that we've noticed as a blocker for other Linux distributions is our minimum version support for glibc. And so there are two different ways to get kind of like Mojo and Max today. One is through their PyPy packages like a pip install max. The other is through Pixie and the Conda ecosystem. And so like in the Pixie and the Conda ecosystem, you can largely create an encapsulated environment and provide a lot of your own dependencies. And so it makes it, a little bit more flexible in terms of the Linux distributions, whereas the PyPy package depends more on some system packages there. So we've seen a few cases where, like, for example, like Ubuntu 2004, if you use like the pip install wheels, our glibc version is incompatible with that version of Ubuntu. So we moved up the glibc version for good reasons like a few months ago. We were running into some incompatibilities. I think we're still like investigating whether we can move that back down. Can we increase the compatibility that way? Or are there other ways to avoid this? So I think we're actively looking into that internally to see if we can expand Linux support in that direction. And then specifically for one of the original asks in this question about Nix and NixOS, we're internally evaluating there are both licensing as well as packaging issues in providing packages for the Nix package manager. So we're actively looking into that internally as well to be able to expand in that direction. For Mojo LSP support, we looked and we saw we see a ton of Vim users working to try to use the Mojo LSP. So like we have it on our roadmap to take a look at expanding LSP support for editors like Vim, and also say that we're investing in the VS Code extension as well to improve the overall experience for that.
One thing I'll also call out regarding the Mojo LSP support. So for those that use NeoVim, there's a popular plugin called LSP config, and there's already support for Mojo, which so you can just have a one-line thing where you set up LSP config and just initialize Mojo. I use this on a day-to-day basis, and so do many other engineers internally at Modular. I'll drop a link in the chat.
Thank you, Joe. And thank you, Brad. Any live questions for the team? Going once, going twice. Okay, well, if there are no other questions, I want to give another huge thank you to all of our presenters today. Really awesome presentations, and we really appreciate it. And we will see you next month at our next community meeting. Thank you.